Physics theories, Mr. Thompson here. Okay, looking at atomic theory and the Thomson model is what we target with charge to mass ratio. Okay, so we'll do some problems on that. Let's take a look at the first one. Positively charged particle travels undeflected through mutually perpendicular electric and magnetic fields as shown. If the charge is traveling at 6.8 e5 meters per second and the magnetic field strength is 770 milliteslas, then find the magnitude and the direction of the electric field between the plates. Okay, so we know that the charge is moving through here. Now the magnetic field, right, is going into the page with the x's, and the electric field must be balancing out, right, the magnetic force with an electric force. So what we do is we equate the two. We equate the magnetic force and the electric force. Now we like to do the absolute value of them because it's really just magnitudes. They're obviously in different directions, okay? And what we can do is we can sub in QVB perpendicular is equal to Q times E, where E is our electric field strength. Okay, what we'll do is we can solve this equation for the electric field. That's what we're looking for. Electric field strength is going to be Q times V times B perpendicular divided by Q, so V, B perpendicular. Put in the speed, 6.8. E5, multiply that by 770, E negative 3. All right, the calculation. .236, so essentially 5.24 E5. And the units here should be newtons per coulomb or volts per meter. So units of an electric field. All right, now how about the direction? Well, for the direction, we need to understand that there is the third hand rule. Now, it's a positively charged particle, so what we're going to do is we're going to use our third right-hand rule for force. And so in the case of the field here, we put our hand kind of pointing in the fingers point in the direction of the field going into the page. Our thumb is pointing over in the motion of the charge, and the palm shows the force. And so in the case of this, we've got the force going towards the top of the page. And so if the magnetic force on this positively charged particle is this direction, then the electric force must be downwards and opposite. Now, if there is an electric force that goes downwards, and it's a positively charged particle, there must be a negative plate down below attracting the charge down and a positive plate above repelling that positive charge down. And so the field must be going from positive plate to negative, and so we'd say it would be down or towards the bottom of the page. Okay? All right, let's take a look at another problem. Question number 2. An alpha particle is entering a perpendicular magnetic field at a speed 4e5 meters per second. If the magnetic field is 290 milliteslas acting out of the page, then determine the radius of its circular path. Okay, well, we have a diagram showing what's happening here. Okay. And so what we can do here is we can equate the magnetic force and the centripetal force, because the magnetic force is causing centripetal force, which is causing circular motion for the charge. And let's put in what we have here. QV, V perpendicular, is mv squared over r. And we're going to solve this one for what we need, which is r. So r is going to be mv over q, V perpendicular. Alpha particle. So its mass, get it from the data sheet. We have 4e5, and the charge of an alpha particle from the data sheet, and the magnetic field strength. Okay, don't forget to put brackets around the bottom, okay, for your calculation. Let's do the thing right here. I'll just divide by both. That's usually what I like to do rather than use brackets. Divide by the first one, then divide by the second one on my calculator. Okay, I get 2.9, pardon me, e negative 2 meters or 2.9 centimeters. Now, whether the path is clockwise or counterclockwise. Okay, so let's think about our hand rule for force once again. So in the first question here, we used our third right-hand rule for force. Here, we're going to be using our third right-hand rule for force again. So I'm going to use my right hand, okay? And in the case of this right here, well, let's take a look at how we'd line it up. We'd have our fingers coming out of the page, okay, so towards you. The thumb goes to the right, and the palm shows the force. So it's coming out of the palm towards myself or towards the bottom of the page. And so in this case here, it should end up going this direction and then circling around. And so in this fashion, what we'd say is it's like the hands of a clock, so it'd be clockwise. So of course, using the third right hand rule for force. Okay. I mean, you can't quite see that. There we go. That's better. All right, thank you.